This video will cover the Hardy-Weinberg Principle as it applies to various genetic problems. The Hardy-Weinberg Principle allows one to calculate the allele and genotype frequencies in a population for various types of genetic conditions that exist. The equation was first developed in 1908 by G.H. Hardy. Hardy was a cricket mate of Reginald Punnett, who developed the Punnett square. And in 1903, William E. Castle, a geneticist, showed that without selection, genotype frequencies would remain stable. Reginald Punnett had seen that this was not accurate, however, could not work out the mathematics behind how to prove his theory. So he incorporated the help of his cricket mate, G.H. Hardy, and Hardy developed the Hardy-Weinberg Principle. That was originally known as the Hardy Principle until around 1943, when it was pointed out that in 1908 a German physician by the name of Wilhelm Weinberg had also come up with the same conclusions independent of Hardy. And so today this is known as the Hardy-Weinberg Principle in honor of the two individuals who developed this mathematical principle to help calculate genotypic frequencies within a population. Now, the Hardy-Weinberg Principle predicts that gene frequencies will remain the same from one generation to the next only if certain conditions are met. And these include that the organism must be diploid, that only sexual reproduction occurs, that the generations are not overlapping, mating is random, population size is infinitely large, the allele frequencies are equal in the sexes, and there's no migration, mutation, or selection. Any violations of the Hardy-Weinberg assumption cause a deviation from the expectations. And so when we look at random mating, humans do not randomly mate, and in some species there's inbreeding, which can cause an increase in the homozygosity for certain genes. Mutations, while they have a very subtle effect on allele frequencies, they do cause a deviation. Small population size can also cause random changes in the allele frequency. When we look at sex-linked traits, because males only have that one X chromosomes, females have two, we're going to see a deviation from the Hardy-Weinberg expression. With that said, we still can use the Hardy-Weinberg Principle effectively in solving various genetic problems. So if we consider an autosomal recessive trait where a middle finger is shorter than the second and fourth fingers, if we know the frequency of the dominant and the recessive alleles, then we can calculate the frequency of the genotypes and phenotypes and trace the trait through the next generation. Simply put, the Hardy-Weinberg Principle is stated as p squared plus 2pq plus q squared equals 1, where p squared equals the frequency of the homozygous dominant genotype, 2pq equals the frequency of the heterozygous genotype, and q squared equals the frequency of the homozygous recessive genotype. Let's apply the Hardy-Weinberg Principle to a series of questions concerning genetics. Now remember, the Hardy-Weinberg Principle is p squared plus 2pq plus q squared equals 1. A lethal recessive condition is responsible for the death of 1 out of every 20,000 babies born in South America. What is the frequency of the homozygous recessive individual in the population? We take 1 divided by 20,000, and this will give us our frequency of the homozygous recessive individual, which is q squared. What is the frequency of the recessive allele? We take the square root of this number, and that will give us Q as being 0.007. How many people out of 1,000 individuals in this population would carry the recessive trait? So the next thing we need to do is find P. And P equals 1 minus Q, so P would equal 1 minus 0.007, which would equal 0.993. Then we can apply that information to 2PQ, which is going to be our carrier state. So we multiply 2 times P, which we've just received, times Q, which we've just received, and we would get 0.014. So if we multiply 0.014 times 1,000, 14 people out of 1,000 carry the recessive trait. In this example problem, we are dealing with snapdragons, which are flowers. And snapdragons, R is dominant for red and little r is recessive for white. Snapdragons exhibit incomplete dominance, where big R, little r would be pink. In a population of 100 snapdragons, 50 would be pink and 25 would be white, 25 would be red. What is the frequency of the heterozygous individuals? Remember, heterozygous will be 2PQ. So if we take the 50 out of 100 stated in our problem, we would get 1/2 or 0.5 as our frequency of our heterozygous individuals. What is the frequency of the dominant allele? Well, P squared would be 25 divided by 100, which would be 0.25. We take the square root of 0.25, and so P would be 0.5. What is the frequency of the recessive allele? Q would equal 1 minus P, or 1 minus 0.5, which would be 0.5. What is the frequency of the homozygous recessive individual? We take our 0.5, square it to get Q squared, and we would have 0.25 as our answer. Here we have a practice Hardy-Weinberg problem where 1 in 1,700 U.S. Caucasian newborns have cystic fibrosis. Now, normal is dominant to cystic fibrosis, which is recessive, so big C will be normal, little c will be cystic fibrosis. We will be using the Hardy-Weinberg equation, P squared plus 2PQ plus Q squared equals 1, where P squared will be homozygous dominant, normal, Q squared will be homozygous recessive, cystic fibrosis, and 2PQ will represent the carrier state. So we want to know what percent of the population are carriers for cystic fibrosis. The first thing we're going to do is calculate our individuals that have cystic fibrosis. We know that is 1 in 1,700. So we take 1 divided by 1,700, and that gives us our Q squared. We take the square root of that, and that gives us Q. P equals 1 minus Q, so 1 minus 0.0223. We get 0.98. I did round just a tiny bit. To get our carrier state, we take 2 times P times Q. We get our answer. Now, to find out the number of individuals, we take our 1,700 times our 2PQ, and so out of 1,700 people, we would expect 76 people to have cystic fibrosis. Percent-wise, it would be 44.5% would carry cystic fibrosis, meaning that 44.5% of the individuals are carriers for the cystic fibrosis trait. Here we have a Hardy-Weinberg problem dealing with dragons, and it's dealing with the wings of dragons. Having wings is dominant to not having wings. When we count the number of dragons present, there are 21. When we count the number of dragons missing wings, we get 7. So to calculate our recessive, which would be our Q squared, we take 7 divided by 21, and we get 0.333. Take the square root of 0.333, and we get 0.577. To get P, we have 1 minus Q, So 1 minus 0.577, we get 0.422. We square this number to get our p squared. Now, if I want to know the likelihood of occurring for q squared, p squared, and 2pq, I can take this and multiply it times 21. It will tell me how many individuals would have no wings. I can take the 64.9%, multiply that times 21, and it would tell me how many I would expect to be homozygous dominant for wings. I would take my 2pq, which is 2 times p, which is right here, times our q, which is right here. So our 2p cubed would work out to be 0.749 or 74.9%. Take this, multiply it times the 21, and I would expect 15.7, or right at 16 of the 21, to be carriers, big D, little d, for wings. Now in this problem, we are dealing with flowers. Genotypes would be big A, big A, big A, little a, little a, little a. The number of plants we will be dealing with is 500, and it's stated in the problem. So out of the 500 plants, 320 will be big A, 160 will be big A, little a, and 20 will be little a, little a. Now if we have 320 plants that have big A, we would multiply 2 times 320 to get the total number of big A's present, which would be 164. Plus, we have to look at our heterozygous, and we would have 160 big A's here. So we add that up, and our total for our 500 plants would be 800 big A alleles. With our little a, because we have 20 plants that have little a, we multiply 20 times 2, we get 40. We also have to add the 160 little a's from this plant, and we would get 200 plants that would be little a, little a. We add up our 800 and our 200, so our total number of alleles or letters for a plant, for 500 plants, would be 1,000. We take 800 divided by 1,000, and our allele frequency for big A would be 0.8, and this would be our P. We take our 200 divided by 1,000, that would give us 0.2 allele frequency for little a, which would give us our Q. And this is how we calculate allele frequencies when asked in a Hardy-Weinberg problem. This is the same problem using the legs of a bird, and in this we have W's to represent webbed or not, and we have no webbed as being big W, no webbed as heterozygous being big W, and webbed feet being little w. Out of 500 animals, 320 were dominant big W, 160 was big W, and 20 was little. So because we have 320 that are big W, we multiply 320 times 2 to get the total number of big W's present. That will be 640. We also have to count this 160 W's right here. We add it up and we get 800. So 160 plus 640, 800. For our little, we have 20. We have to multiply 20 times 2, so it gives us the number of W's here and there, and that's 40. Plus we have to add the little W's here, which is 160. That gives us 200. We take our 800 plus our 200, so our total number of alleles or letters would be 1,000. You can also get that by taking your number of animals times 2, because each animal has 2 letters. We take our total number of big W's divided by our total number of alleles, and this gives us our allele frequency for big W as 0.8. This would be P. That would also give us our allele frequency of 200 divided by 1,000 for little w being 0.2, which would be Q. Here we have the binomial theorem where we have a plus b squared equals a squared plus 2ab plus b squared. We can use the Pascal triangle to help us with expanding our binomial theorem. The way the Pascal triangle works is we write a 1 here, we come down, we write a 1 and a 1. We come down and we write a 1, and we write a 1 on the outside. To get this middle number, we take that 1 plus 1 equals 2. Next layer, we put a 1 and a 1, and then for our middle, 1 plus 2 is 3, 2 plus 1 is 3. We come down to our next level, we put a 1 and a 1, 1 plus 3 is 4, 3 plus 3 is 6, 3 plus 1 is 4. We come down, we have a 1 and a 1, 1 plus 4 is 5, 4 plus 6 is 10, 6 plus 4 is 10, and then our 4 plus 1 is 5, and this continues down. So that when we use the binomial theorem, if we were to expand a plus Now here we have the binomial theorem again with our triangle that we just explained on the previous page. And so a plus b to the 0 level would be 1. A plus b to the first would be a plus b. A plus b squared would be a squared plus 2ab plus b squared. A plus bq would be a cubed plus 3a squared b plus 3ab squared plus b cubed, etc. Now we got this information from that previous Pascal triangle, and that's taking our binomial theorem and expanding it. We can apply this information to help make predictions in genetics problems. So again, here we have our Pascal triangle for us to use. We're going to show you how this applies to a typical genetics problem. So starting off, we have two parents who are heterozygous carriers for albinoism. We have our Punnett square, big A little a crossed with big A little a. We get 1/4, that would be big A, which is p squared. We would get 2/4 or 1/2 being big A little a, which would be our 2pq, and we would get 1/4 as being little a, or q squared. We want to know what are the chances that an individual couple would have 3 children, 2 would be carriers for albinoism, and 1 would be an albino. So here we have the Punnett square from the previous slide, and we also have our Pascal triangle. And so what we want to do is we're dealing with 3. So we're going to come down because of 3 children to this level, and so we're going to be doing the 1, 3, 3, 1. And that expands to a cubed plus 3a squared b plus 3ab squared plus b cubed. Now we're going to say that A is going to be a carrier, and we're going to say B is going to be the recessive. To be a carrier, that would be this box and this box, which would be 2/4 or 0.5. To be the recessive, that would be 1 out of 4, which would be 1/4 or 0.25. So we're dealing with 3 children, 2 are carriers, and 1 is albino. We multiply 3 times 0.5 squared times 0.2, and we would have an answer of 0.125, or a 1 in 8 chance of the couple having 3 children, 2 as carriers, 1 is an albino. Here we have a Hardy-Weinberg problem where we have worked out the Punnett square, and we've crossed a heterozygous big A little a with a heterozygous big A little a. We would have 1/4 being big A, 2/4 or 1/2 being big A little a, and 1/4 being little a, little a. What are the chances of having 5 children, 2 are normal and 3 are afflicted? Now, With our normal, we have all of these being normal because it did not say that we could not count carriers who appear normal. So normal would be 3 out of 4 or 0.75. We have this one right here that's afflicted, which is 1 out of 4 or 0.25. If we apply that to Pascal's formula, his triangle, we're dealing with 5 children, so we come down to the 5. Now we're going to take this right here and we're going to expand it. When we do so, we have it right here, where a plus b to the 5th is going to be a to the 5th plus 5, a to the 4th b plus 10, a to the 3rd b squared plus 10a squared b to the 3rd plus 5a b to the 4th plus b to the 5th. So we have 5 children, 2 are normal, 3 are afflicted. We will let a be normal. So we will use this area right here because we have 2 that are normal, 3 that are afflicted. So we have our 10 times our normal, which is 0.75 squared, times our afflicted, which is 0.25 cubed. We got that from here. We have an answer of 0.0878, or about 8.8% chance of there having 5 children with 2 afflicted, or 2 normal, 3 afflicted.